The oldest meteorites and lunar rocks are said to be about 4.5 billion years old, but the oldest Earth rocks currently known are 3.8 billion years old. Sometime during the first 800 million years or so of the Earth's history, the surface of the Earth changed from liquid to solid. Once solid rock formed on the Earth, its geological history began. The present is the key to the past. We know this because of relative and absolute dating. Relative dating principles include quite a few laws. One would be superposition. In a sequence of rock strata, the oldest layer will lie below or underneath the youngest. Another one would be the law of original horizontality. Layers of sediment, such as you would have at the bottom of a lake or ocean, are deposited by gravity into flat layers. A law of cross-cutting. If a rock layer is cut by fault or igneous intrusion, the rock that is cut must be older than the layer that cuts it. The law of lateral continuity is rock layers will extend outwards until the environment that produced them changes. On the other hand, there's absolute dates for rocks, which are usually obtained by determining how many half-lives of a radioactive parent element have elapsed since the sample originally crystallized. A half-life is the time it takes for one half of the original unstable radioactive parent element to decay into a new, more stable daughter element. The geological time scale was developed primarily during the 19th century through the efforts of many people. It was originally a relative geologic time scale, but with the discovery of radioactivity and the development of radiometric dating methods, absolute ages were added in the beginning of the 20th century. The rock cycle is a pictorial representation of events leading to the origin, destruction, or changes and reformation of rocks as a consequence of Earth's internal and surface processes. There are three major types of rocks: igneous, which result when magma or lava crystallize, or when volcanic ejecta such as ash accumulate and consolidate. Sedimentary rocks, which form one of three ways: consolidation of mineral or rock fragments, precipitation of mineral matter from solution, or from compaction of plant or animal remains. There is also metamorphic, which results from the alteration of other rocks, usually beneath the surface by heat, pressure, and chemical activity of fluids. Solidification of the molten material into rock happens as the Earth cooled. The Earth's oldest rocks are currently known as 3.8 billion years old. The continental drift is the gradual movement of the continents across the Earth's surface through geological time. Continental drift describes one of the earliest ways geologists thought continents moved over time. Today, this theory has been replaced by the science of plate tectonics. There are three different types of plate boundaries: divergent, convergent, and transform plate boundary. A divergent boundary occurs when two tectonic plates move away from each other. Along these boundaries, earthquakes are common, and magma rises from the Earth's mantle to the surface, solidifying to create new oceanic crust. When two plates come together, it's known as a convergent boundary. The impact of the colliding plates can cause the edges of one or both plates to buckle up into a mountain range, or one of the plates may bend down into a deep seafloor trench. A chain of volcanoes often forms parallel to convergent plate boundaries, and power earthquakes are found common along these boundaries. At convergent plate boundaries, oceanic crust is often forced into the mantle where it begins to melt. Magma rises into and through the other plate, solidifying into granite, the rock that makes up the continents. Thus, at convergent boundaries, continental crust is created and oceanic crust is destroyed. Two plates sliding past each other forms a transform plate boundary. Natural or human-made structures that cross a transform boundary are offset, split into pieces, and carried into opposite directions. Rocks that line the boundary are pulverized as the plates grind along, creating a linear fault, valley, or undersea canyon. Earthquakes are common along these faults. In contrast to convergent and divergent boundaries, crust is cracked and broken at transform margins, but is not created or destroyed. A few examples: Yosemite National Park. As the North American plate overrode the Farallon plate, a process geologists called subduction, this plate was pushed several miles beneath North America, where extreme heat and pressure melted its leading edge. Vast pools of magma rose up under California, some of which reached the surface to form volcanoes. Yellowstone National Park. About 2.1 million years ago, the movement of North American plate brought the Yellowstone area closer to shallow magma body. And then there's the Hawaii Volcanoes National Park. Hawaii is geologically a unique place on Earth because it's caused by a hotspot. A geological hotspot is an area in the middle of a crustal plate where volcanism occurs. The molten magma breaks through the crustal plate, which essentially is how the Hawaiian Islands were created. Faults occur when energy is suddenly released, usually as the result of displacement of rocks along fractures. There are three types of faults that can occur. Dip-slip faults. All movement is vertical, taking place up or down the dip of the fault plane. Normal faults are caused by tensional stress. Reverse and thrust faults form in response to compression. Another type of fault that can occur is a strike-slip fault. All movement is horizontal and due from shear stress. And then there's oblique slip faults, which occur when there's a combination of both horizontal and vertical movement at the same time. In geology and oceanography, transform faults occur when two tectonic plates slide past one another. Although they neither create nor destroy land, transform boundaries and strike-slip faults can create deep, shallow earthquakes. These are common at mid-ocean ridges, but they do not normally produce deadly tsunamis because there is no vertical displacement of the seafloor. Continental transform boundaries other than California include the North Anatolian Fault of northern Turkey, the Alpine Fault crossing New Zealand, the Dead Sea Rift in the Middle East, the Queen Charlotte Islands Fault off western Canada, and the Magalhães-Fagnano Fault System of South America.
In the United States, there are many, and they're in parts of the country you'd never expect, not just California, but places like Missouri and Tennessee. So how many Americans are in danger, and what if a huge quake hits here? Sam Champion is on the New Madrid fault line in Memphis, where there was a tremor just over the weekend. Sam?
Yeah, and George, the interesting thing about the New Madrid Fault, which was one of those surprising ones, is it runs from Memphis all the way into St. Louis. So there are millions of people right in the middle of the country that are affected by that. But we went to the top seismologists in the world to find out that there actually were historic earthquake events in the United States. And believe it or not, earthquakes happen here just about every day.
The thing with earthquakes is it's location, location, location. So as we saw with this devastating earthquake down in Haiti, that was a magnitude 7 rupture, but more to the point, it was directly underneath very large population.
Just like California, where most Americans may think all our earthquakes are centered. But California's San Andreas is just one fault zone. There are at least 4 active earthquake zones that cover this country, all of which seismologists say have had historic eruptions, and each could have another catastrophic strike at any time.
Earthquakes are a national hazard, and it's in these areas away from California, away from the places we think about, where there can be some of the greatest risk.
What about America's heartland? We're on the second most active fault in the country, and that's the New Madrid Fault. It runs from St. Louis to Memphis, and this is Reelfoot Lake, 16 miles long and created 200 years ago by what is still today the most powerful series of earthquakes in American history. It happened nearly 200 years ago on the morning of December 16th, 1811. An estimated 7.5 on the Richter scale. It was followed by a series of 2,000 aftershocks over the next 5 months, some measuring 8.0 and felt as far away as Boston. New Madrid is the biggest fault line east of the Rockies. It extends 120 miles through 5 states, cuts across the Mississippi River in 3 places, and slices the Ohio River in half. Even now, the area averages a tremor every other day. A major earthquake here would affect 15 million people in 7 different states.
Do we think there's a big earthquake on the way for this zone?
Yes, we have a history of large earthquakes that have occurred here at least over the last 1,500 years, about every 500 years. And those earthquakes occur as large sequences of events, not just a main shock.
New York, New Jersey, and Pennsylvania have the 70-mile-long Ramapo Fault. These streaks are really all that's visible of the Ramapo Fault, and they continue all the way up this rock. It's one of the largest in the Northeast, and we're really just about an hour outside of New York. Never heard of it? Well, it's been quiet for a couple of hundred years, and seismologists say that's part of the problem.
We know in the future at some point an earthquake is going to occur, but we don't really understand the rules of the game yet in this area.
What we do know is the last major activity on the Ramapo Fault was a 5.2 centered in Brooklyn, New York in 1884. And if that same quake hit today, there are now 8 million residents of New York City. All could be affected by the Ramapo Fault's dangerous reach.
One important fault is the one that crosses Manhattan from the Hudson River to the East River, more or less along 125th Street. That's a well-known fault. There are tunnels constructed for the water and for the subway lines underneath that cross this fault.
And of course, there are 2 other hotspots. One, a subsidence zone that's just off the Pacific Northwest coast. It's in the water, but it's pretty active all the time. And the granddaddy of them all is the San Andreas Fault. There are thousands of earthquakes there every year. George?
Hey, Sam, thanks very much.
That was fascinating, Sam. Thank you. You said
A volcano is a hill or mountain that forms around a vent where lava, pyroclastic materials, and gases erupt. It's a landform. It's a feature on Earth's surface. There are 3 main types of volcanoes. One is the shield volcanoes. They're composed almost entirely of low viscosity mafic lava flows that looks much like the outer surface of a shield laying on the ground with the convex side up. They are most commonly found in the ocean basins. The big island known as Hawaii is made up of 5 huge shield volcanoes. Another type is the cinder cone volcanoes. These are smaller, steep-sided volcanoes made up of pyroclastic materials that resemble cinders. According to National Geographic, a few places we can find shield volcanoes include Capulin Volcano National Monument, Lassen Peak National Monument, and Sunset Crater Volcano National Monument. The last type is going to be composite volcanoes. They're also called stratovolcanoes and are made up of mainly of lava flows and pyroclastic materials of intermediate composition, although mud flows are also common. National Geographic provided me with a few places where composite volcanoes are located. Mount Rainier up in Washington, Mount Shasta here in California, and Mount Katmai up in Alaska. Volcanic eruptions can be predicted by monitoring them, which involves recording and analyzing physical and chemical changes. Geologists use multiple things. I'll list quite a few. Gravity and magnetic field studies, temperature measurements, satellite remote monitoring, ground deformation studies, GPS measurements, direct gas sampling, lava sampling collections, remote sensing of gases, and studies of the past. Predicting eruption is done mainly by monitoring, forecasting, and detecting volcanic tremor.
Prime suspect is plain to see. The awesome Kilauea volcano.
We like to call Kilauea the most active volcano in the world because it's been erupting continuously since 1983. It has been going every day, almost non-stop since that time.
The lava is so hot, it burns a channel into the rocks beneath it. Hundreds of these expressways crisscross the island, carrying lava underground up to 30 miles until it reaches its inevitable destination, the ocean.
When the lava hits the ocean, it's extremely hot, and it shatters into lots of little pieces. So what it does is leave a lot of black sand behind it.
Layer upon layer of this black sandy rubble slowly piles up on the ocean floor until it forms a new beach. New lava on the surface runs across this beach, cooling slowly to form a new piece of solid land on sandy foundations. This massive island is built on piles of loose rubble.
Earthquakes are defined as the shaking or trembling of the ground caused by sudden release of energy, resulting in faulting, and involves displacement of rocks along fractures. About 80% of all earthquakes happen in the Circum-Pacific Belt, a zone of seismic activity nearly encircling the entire Pacific Basin. Seismic waves include two major types of waves: body waves and surface waves. Body waves include primary waves and secondary waves. Primary compress and expand material in the same direction they travel. Secondary waves move material perpendicular to the direction of wave movement. There's also Rayleigh waves, move material in an elliptical path in a plan oriented parallel to the direction of wave movement. And then there are love waves, which move material back and forth in a horizontal plane perpendicular to the direction of wave movement. An earthquake's epicenter is determined by using a time-distance graph of the P and S waves to calculate how far away a seismic station is from an earthquake. 3 seismic stations are needed to locate the epicenter. Although earthquakes cannot be predicted, geologists use analysis and historic records and the distribution of known faults to construct seismic risk maps when anticipating future earthquakes. So the San Andreas Fault is a transform fault separating the Pacific Plate from the North American Plate. Movement along the San Andreas has caused thousands of earthquakes, especially in California. These type of transformation faults can cause displacement from tens to hundreds of kilometers. Geologists believe that the San Andreas came into being about 15 to 20 million years ago. Studies of a segment of the fault between Tejon Pass and the Salton Sea revealed geologically similar terrains on the opposite sides of the fault, now separated by 150 miles. Studies also show that crustal blocks have moved through more than 20 degrees of latitude. Surveying shows a drift at the rate of 2 inches per year. A major earthquake with a magnitude of 7.9 occurred on April 18, 1906 at 5:12 a.m. off of the northern California coast near San Francisco. Some 700 people originally were thought to have died in the disaster, but the death toll is now believed to have exceeded 3,000. Moreover, about 250,000 were left homeless. Survivors camped in Golden Gate Park and dunes west of the city or fled to outlying towns. As such, recent predictions limit the possible maximum earthquake magnitude along the San Andreas fault system to be 8.0, although a 7% probability estimate that such an event could occur in Southern California in the next 30 years.